Hello guys, we are 2 weeks away from being done. We have some work this week and some work next week, and then we are good to go for the summer so long as you've been doing what you're supposed to be doing. Today we're going to talk about volume of prisms and density, and then we'll do a little bit of practice, and then we'll call it a day. So, a prism. A prism is a three-dimensional solid object with two identical ends and flat sides. The two identical ends, or the two identical faces, would be the shape that is used to generate the name for the prism. So if you look at the very first picture we have here, the front and back would be triangles, and the sides, which are called the lateral faces, would be rectangles. All prisms will have rectangular sides and two congruent bases. This would be a triangular prism because the base is a triangle. The second one here would be a square prism or cube because the base is a square, front and back, and all the sides are also squares, which means they are also rectangles, which fits the definition of a prism. The third one here, the base, notice we have lateral faces or sides that are rectangles, okay? And we have 1, 2, 3, 4, 5-sided base and rectangular sides, pentagonal prism. And then we have a hexagonal prism because 6 sides, hexagon, hexagonal prism, octagonal prism, and this is a decagon, decagonal prism. But the key thing is that the bases are the two identical sides. Now, base, sometimes students get confused with the difference between the base and the bottom. So the base is not the bottom of the shape. If you look at our first example, the triangular prism, the bottom, the side that it's actually sitting on, if it was sitting in front of you on the table, the bottom is the rectangle. But the two equal parallel sides would be the triangles, are the bases. So off on the right-hand side here, this is a pentagonal prism because the base is a pentagon, and at the bottom, on the other end, is a congruent parallel base. So it doesn't matter if this object was sitting in front of you on the table, it doesn't matter which side's the bottom, that's not the base. The base would be the two congruent parallel faces, two congruent parallel sides. All right, so what you remember probably is volume of a rectangular prism, length times width times height. That's the one from middle school that was drilled into your head, length times width times height. That works for a rectangular prism because the area of the rectangle base is length times width, and then when you add the third dimension to make it a brick or a shoebox or something, then you also have the height, length times width times height. In general, for any prism, the formula for volume is BH, but in this case, the B is a capital B, and the capital B represents the area of the base shape itself. So that's why we need to know which side is the base shape, because we want the area of that base shape and then times the distance between the two parallel bases. That would be our height. So if we look back at our first picture here of our pentagonal prism, we have a pentagon base, so we would have to do the area of the regular pentagon with the apothem like we talked about last week or 2 weeks ago. We would do the area of the base, that would be the capital B, and then we would measure or get the height between the two bases to find the volume. It's almost like finding the area of one single card in a stack of cards and then multiplying it times 52 to get the volume of the full stack. So it's the area of the base times the height. So we're just going to practice that. And then if you think you don't need me anymore, then go ahead and practice on your own. You can always check the answer key to make sure you're doing things right. Or just stay tuned and we'll do some of these together and have a grand old time. Okay, so our first example, we have to find where is the base. So our base is a triangle with dimensions height of 9, length of 12. So what we're going to do is look at our volume formula, area of the base times the height, the base shape, the two congruent parallel sides that are not the rectangles, would be this triangle. Now this triangle, we know the formula for the area of a triangle, base times height divided by 2. So our volume starts with the area of the triangle, 9 times 12 over 2, and then multiplies it times the height. Now the height of this prism is the distance between the two parallel bases. So in this case, the distance from one triangle edge to the other triangle edge, that's our height of 10. So we go to our calculator, multiply this out, and we end up with a volume of 540 centimeters cubed because it's a three-dimensional shape. All right, try number 2, and then come back and check your work. Or just stay with me, and here we go. Again, the base shape, the shape that has two parallel congruent sides, is another triangle. This one has dimensions height of 3, base of 4, and then the height of our prism from one triangle to the other, one side to the other side, is 6 centimeters. So we do base times height divided by 2. 3 times 4 is 12, divided by 2 is 6, times another 6, and we get a volume of 36 cubic centimeters. So what if we had something that was drawn on a three-dimensional coordinate grid? Now this is something that you haven't seen before, but it's pretty cool. What you're used to is X and Y. But eventually, as you go into better, more fun, cooler math, you'll get to three-dimensional graphs, like what you see here. X-axis and Y-axis, and then the Z-axis, X, Y, and Z. So what you do is you can just look at the dimensions or units, 1, 2, 3, 4, 5. So that means our edge AB is 5 units long, and then 1, 2, 3, 4, our height would be 4 units high, and then the depth or the width, 1, 2, 3, is 3 units. Now this being a rectangular prism, you can just do length times width times height. It doesn't matter because all sides are rectangles. It doesn't matter which one you consider the base because all rectangles have the same area formula of length times width. So in this special case, it's like the middle school problem that you learned, length times width times height. And the commutative property says it doesn't matter the order in which you multiply all these things. So it's 60 units cubed, 60 cubic units. Now, one of the practical applications of volume is density. So you were expected to know the density formula from your work in your science classes. Density is mass, which means weight, divided by volume. All right, so density is the ratio of the mass. Density is the mass divided by the volume. Ratio means written as a fraction, so we are doing mass over volume. So which has more density, 1 cubic foot of styrofoam or 1 cubic foot of concrete? The answer is concrete, because it weighs more, so it means it has a greater mass. Mass is basically what we do use as height, or weight, I mean, sorry. Okay, so let's do an application question. Pure gold has a density of 19.32 grams per cubic centimeter. A pawn shop owner says they have a gold cube with an edge length of 2 and it weighs 145.32 grams. Is it really pure gold? So what we can do is take our density formula, mass over volume. The density is supposed to be 19.32 grams per cubic centimeter. This person is telling us that it weighs 145.32 grams. That's our mass. And if it's a cube with an edge length of 2, then we can get the volume, and we can determine whether this is truly pure gold by testing the density and see if it comes out correctly. So if I do this 145.32 divided by 8, we get 18.165 and not 19.32. So the answer, is it pure gold? No, because the size and the weight does not give us the same density as pure gold. So try a similar example with silver and Pam, and we'll see how you do. So you can pause it, you can try the problem, and then you can turn it back on and see how you did. So we are told that the pure silver has a density of 10.5 grams per cubic centimeters, and we have a coin that is 4.746 grams. Let's figure out what the volume should be. So we can just cross multiply. Then divide. And our volume, the cubic centimeters, based on the density units. All right, so the last thing I want to do is just look over how to do a composite calculation. Just like we did composite area, what we have to do is take our shape, break it up into smaller parts, find the volume of the smaller parts, and then add them back together. So pause it, pick a problem, just one of them, try it, and then I'll show you what the answers are. Okay, so you can break this up several ways, but based on the lines that are already there, it's kind of obvious how I'm going to break it up. You just need to figure out what are the dimensions. So based on the 6 centimeters at the top and the 10 full length along the bottom, I know that edge is 4. So for shape number 1, my volume is 4 times 3 for the base, because I know my width here is 3, and then a height of 4. So that's 12 times 4, which is going to give me 48 cubic centimeters. The bottom portion is a length of 10, height of 2, width of 3. So it'll be 2 times 3 times 10, which is 60 cubic centimeters. So my overall composite volume for the whole shape, add those together, 108 cubic centimeters. And then if you chose the second one, again, it's kind of obvious how I broke this up, because you can see where the division lines are. Looks like 2 blocks, one on top of the other. So the volume of the top half, smaller piece on top, would be 8 by 3, and then 6 meters tall. So that ends up with 144 cubic meters. And then the bottom portion, we're going to do a similar calculation. 10 by 3 by 6. So 10 times 3 is 30. Times 6 is 180. So the bottom portion is 180 cubic meters. Then we're going to add those together. We get our final volume of 324 cubic meters. All right. So that's volume. Guys, I'll talk to you in a few days. Hope you're doing well. Take care, stay healthy, and be good.